Okay, so let's start with half-life. Now, half-life is used a fair amount in medicine, nuclear chemistry, let's see, what else? Geology. Quite a number of things. And basically what it is how long does it take for the initial mass to decrease by half? So, if you take differential equations, this is the first example you run into. It's here. Take linear algebra, the first example they give as balancing equations, the matrices. So anyway, so half-life, who's heard of half-life? What context?
Medication.
Medication. It's used frequently in medication. So, say the half-life is 1 minute. And the half-life is 1 year. Which is more stable? Which one?
The 1 year, I would assume.
The second one?
The 1 year, yeah,
Yeah, why? That's correct.
because it has a longer shelf life.
Right. And it's because one's more stable than the other. Again, stability comes into the picture. So the less time it takes for that mass to go down, the more unstable it is, because it wants to become more stable by getting rid of stuff. That could be beta decay, beta radiation, gamma radiation, alpha, any of those give you in the decay mode, will give you a half-life scenario. Now, some things are really bad. During World War II, the Manhattan Project figured out how to make plutonium. And that's 94 PU. Now, milligrams of this stuff will cause leukemia. And up at Hanford, in Washington State, they have a facility there that started in World War II, the Manhattan Project. They were part of it. And their reactors make plutonium. The problem with that is a lot of voice problems. And milligrams can basically kill you. A very short-lived leukemia. Yet we produce pounds up here in Hartford, Hanford. So anyway, the half-life for plutonium is like 10,000 years. It's super stable. The bad part is it's super dangerous at the same time. So you got to deal with this thing for 10,000 years. You start with a pound. After 10,000 years, how much do you have? A half pound. Still got a half pound. After another 10,000 years, now you have a quarter pound. Another 10,000 years, you've got 12.5 pounds of this highly dangerous element. Now, some of these cast uranium are man-made. That's why they got the parentheses. And those half-lives are tiny. And we're talking like microseconds, milliseconds, because they're so unstable, unlike plutonium. So anyway, let me show you how that works. Okay, so by definition, half-life is all right, you just say this better. Okay, time it takes for the initial mass to, let's see. Okay, the time it takes for the initial mass to reduce to 50%. And then each time a half-life goes, whatever they started with is reduced by half. Now, I'm going to do the calculations two ways. You may choose the way you'd like to do them. All right. The abstract way, which is gives you the most flexibility, this is what it is. Okay, so you have the mass after a certain time period times the initial mass, that's n sub 0, times 0.5 to the t over t sub 1/2. Okay, so t is equal elapsed time t sub 1/2 is half-life, and that half-life can be in any units of time, microseconds or centuries. Doesn't matter, as long as it's a time unit. Okay, then we've got n sub t, and that's whatever the mass is at the time that you specify elapsed time. So these two are kind of close. And what's left over here? Oh, we have okay, 4 variables. Elapsed time, n sub t is the time after time had passed. Half-life is a time it takes for 50% of the original initial mass to be decreased by 50%. And then n sub 0 is what you started with, mass-wise. Okay. Now that's the fancy way to do it. And this problem, because it involves exponents in the, if the variable's in the exponent, you've got to use logarithms to solve it. So we're not going to do that equation. I'm going to show you how to do it if you're interested. We're going to be doing a more graphic approach. All right, so let's start with £5. And well, we should probably use 5 kilograms. We're in a metric family. Okay, and so what we start with is 5. And let's say the half-life is 3 years. What is the mass after that? Okay, so and we got initial mass. Oh, we need elapsed time. Okay, so let's look at this on a timeline. Okay, we're going to start right here. That's our initial mass, n sub 0. And we go three years. Oh, that was some sneeze, excuse me. What is our mass here? So 3 years has elapsed. We're starting with 5 kilograms. So what is our mass after 3 years? Half, right? Yes, 2.5. I mean, 2.5, kilograms. And this is 1 half-life right here. Okay, so let's go to another half-life. Okay, so that's going to be 3 years. What's our new mass? 1/2 of 2.5, right? So that's going to be 1.25 kilograms. So how many half-lives have I gone through?
2.
Two. Okay, and we're looking at what was the problem? And the elapsed time is going to be, for this problem, let's say 9 years. Okay, so in other words, we're starting with something that weighs 5 kilograms. After 9 years, with the given half-life of 3 years, what are we left with? Well, how many half-lives have we gone through? 3 plus 3 is 6, not 9, so we got to do another 3. So what do we end up here?
165.
625. So total time is going to be 9 years, elapsed time. And we've gone to 3 half-lives. Each time we go through a half-life, goes down by half. Now, if we were to use the other method, so we want to solve for how much is left over. We have the initial mass times 0.5, and that is raised to T over T sub 1/2. So that's equal to the initial mass was 5 kilos. And the time was 9 years. Half-life is 3 years. How much mass do we have after that elapsed time? So the problem is exponential stuff. So using PEMDAS, remember, PEMDAS, we do the exponential stuff first, which also happens to be parentheses. So we've got okay, and 9 over 3 is 9 divided by 3 is 3. All right. So that's what the mass will reduce down to. So I'm going to do the exponentiation first. times 5 equals. Okay. Same number. Now that's as straightforward as it gets using the formula. And the reason why I said that is because if you have a variable as an exponent, you've got to undo the exponent in the variable by using logarithms. So this is the simpler of the two versions. So if you don't know the half-life or you don't know the elapsed time, you're gonna have to solve this using logarithms. So which of these two do you like better?
Formula.
Who said formula? You did? You did? Oh, okay.
Is that the right answer?
Yeah, we always have right answers on here. Okay, so let me show you another problem using the formula. Just so that you have a feel for this. My cough is getting worse again.
So ginseng tea, the worst ginseng tea.
Hmm?
Ginseng tea.
Do you have any on you?
Not on me, I'll get you some tomorrow.
Okay, so let's do another problem here. We can do it both ways. Maybe. Okay, this time we don't know the elapsed time. Let's go with 3 years again. And our initial mass was 1 kilogram. Is it 1 kilogram we started with? 5 kilograms. And okay, so we don't know the time it takes to take that 5 kilograms and half-life it down to 1. How many years does that take? So we've got our okay. So if you had kind of a not advanced algebra, but a kind of a medium algebra, how would I solve this?
Pretty good thing.
Solve for t. How would I do that? All right, so let's divide both sides by 5. Okay, so now we're left with this. Now what are we gonna do? So we can simplify this. 1/5 is 0.2. 20%, one is 20% of 5. Okay. So there is a law of logarithms that says so we took the log of a to the 6. That's the same value as 6 times the log of a. Okay, so now let's say this was this part here we're going to use there. Okay, so we've got
Wait, where did you get the 6?
Hmm?
Where did you get the 6? It was just.
I just made it up. A to the 6th power. So this was the law we're using now. So this is a log law. Not a mother-in-law. Hey, log law. Okay, so we're going to do this here now. So we're going to take the logarithm of both sides. Okay. I'm going to continue simplifying it. So now I'm going to take this and move it outside. Okay, now we're going to solve for t. So if we divide both sides by the log of 0.5, those cancel. Okay, so now we have t over 3 is equal to the log of 0.2 divided by the log of 0.5, all times multiplied by 3, so the 3's cancel. So that's our answer. So we just throw that into our calculator. That's 3 times log of 0.2, all divided by log of 0.5. So our time, the elapsed time to go from 5 to 1 is years. So you can see why I showed you the graphic method. Now, the disadvantage on using the graphic method, the half-lives have to be whole. They can't be fractional. So the problem is solving a problem when the exponent is in the, or when the variable is in the exponent, you gotta use logarithms. And a lot of people don't like logarithms. So if you don't want to use the graphic method, you can use this method. Totally up to you. And you get the same answer. Okay, so let's do another one using the, are there any questions about this? Or have I convinced you not to use it? Okay, now this is something I invented, this graphic method. And most students get it. Okay, so let's say we're looking for, okay, so let's say we're looking for half-life. No, let's not do that. Let's define half, let's say it's 3 years again. And we want to know how long it took to a given half-life. So the initial amount is going to be 5 kilograms. And it went down, let's say, that's basically the same problem. Let's put, okay, so we don't know the time. How much time does it take to get to 0.3125 kilograms, starting with 5 grams as the initial mass? Okay. So we're starting with initial mass of 5. And then let's go 1 half-life. That's going to be 3 years. And if we started with 5, after 3 years, how much do we get? Half of 5 is,
2.5.
Wait, quick question. Are
Yeah.
you gonna make us do both methods or we're just gonna do one?
one of your choice. No, I just wanted to show you both methods. Okay, so now we're at 2.5 kilograms. Let's go another half-life. That makes it at 125. Half of 2.5 is 1 1/4. We're not there yet. We need to go to the initial breakdown of 0.3125. Okay, we're not there yet. So we need to go another half-life. And half of 1.25 is the 625. Okay, we're not there yet. Got to do another half-life. And half of 0.62 or 0.625 is going to be 3. What? 3. And that's going to be right here. So how long did it take to get to 0.3125? We had to go through 4 half-lives. Each one is 3 years. So 4 times 3 is 12. So the timing on this is going to be 12 years. Are you trying the wild one?
Actually wrote it was the 3 years plus. When I did it.
Yeah.
For the problem that we did for this, the 6.5 years, is how am I visual scale get to something that's.
That's the con of the graphic. That's the base. Use formula.
Use the form down.
Study the formula of the page. The other one. That's me.
But I don't know. This is for a feature.
Here. Okay, while she's copying that down, we're gonna talk about, now this week we're gonna have a test on Thursday. So today and tomorrow, I'm gonna cover what you need to do the lab. And after that, there will be study sessions. Okay, next week will be your final on Wednesday. Okay, so that means on Monday is another study session. We can do it here, out there, or at home. And then on Tuesday, I'm gonna go over your practice tests. Now, to study for the final, I'm just taking the two test 1 and test 2 questions out. But theoretically, it's not gonna be anything new. Okay? So the practice tests for the final is gonna be test 1 practice test, test 2 practice. Because the questions are gonna come from the manual. Does that make sense?
Yes.
And then start making sure you have good progress on your projects also. Okay, so any questions about what we're doing in the last part of this? I realize summer school is
Fast.
half the time has with all amount of return, half the time. 16 weeks, June and 8. Small like the week, like the right. Oh. Okay, so. Now, one of the big factors.
Wait, can
Can
you
you show us?
do that last question with the formula?
Yeah, the law of logarithm form of. Can we see that the law of logarithm apply to the last problem you just did, the example of the 12 years?
I'm not sure which. From where?
Oh, we're just wondering if you could just show us the example of how you got to the 0.3125 kilograms using those other formulas, not the graph.
This one here?
Yeah.
No.
Initial one you had showed us,
What?
or the law of logarithm. As if you were putting it into your calculator, if you were
Oh,
going to
all
put
right.
it in your calculator for the log.
Okay, so we're gonna go 3. It depends how your calculator does logarithms,
It
so,
was weird, I did not.
because logarithms on Casios are different than on Texas Instruments, and they're. All right, so the way I would do this, you're saying, how did I work this problem here, right?
Yeah.
Okay, so we have 3 log 0.2 over log 0.5, and that equals t. Okay, so you're gonna go 3 times log of 0.2 close parentheses, divided by log 0.5.
Is it?
Yeah, so it's 6.9657. Just kept it simple, make it, I guess if you round, it should be,
I thought, Professor?
Yeah.
What is it? I just need to sit this on my own, but. So over here, the time's missing. In this formula. And then on your practice test, the mass is missing. So.
So wait a minute,
either
let's-
way,
so which one, the one I just did, right? You're talking about?
yeah, because this one, trying to solve for time.
Yeah, okay,
The mass is missing. Of the kilograms.
we haven't gone over the practice test yet.
Jack was ahead of
But
us.
then when you're doing mass, it looks like you're just having it. You don't have to.
Instead of using logarithm,
Yeah, instead of using, it, you just kind of have it, right?
the reason we use logarithms is because we have a variable in the exponent.
Gotcha.
And then if it's in the exponent, we can then bring that outside the logarithm. And then that gets it out of the exponent. So now it's just plain old algebra problem. That better?
Yeah.
So a to the sixth, a to the sixth is the same as 6 times the log of a. Let me do another example of that.
Oh, I got it.
Well, I'll give you another really easy example here. Okay, so let's look at 25. 25 is 5 squared, right? Okay, if you look up 5 squared, you already know it's 25. But if we did 2 times the log of 5, what would that be? That was too simple of an example. I took. The main thing on this is if you have an exponent. You can bring it out to here.
Oh, yeah, okay.
Is there a reason why? You can just move it? Just how it is.
No, it's because, you have to get that variable out of the exponent,
You can just move, shift it over.
then you can shift it over. Now, this applies only if the variable, either the time or the half-life time is missing. Otherwise, you don't have to worry about using logarithms.
I think that was my question.
Oh,
This,
when-
the mass was missing on the test. And I was wondering if I should use this formula or just, do the half.
on the practice test, either one will work.
But this will still work even if mass is missing?
Can
For
you
which,
show?
for which mass are you talking about?
What's this final mass? What's this final-
N sub t is the final. Is the of 0 is the initial. You have two masses. Where you're moving along on the timetable and the initial mass. So on that practice test. I made sure it was multiples, full multiples, so you could use either one.
So we're still finding mass, it just depends
Well, it
on,
depends what's missing.
yeah, the initial or the final.
Yeah, so there's initial, final, mass. Then there's elapsed time. That's just plain old T, and then we have the half-life, T sub 1/2. Which I did,
And which one did you,
well, they're the 4 variables. And one of them's gonna be missing.
okay,
I'm gonna stick it in that formula.
okay.
Well, this whole thing. I'm gonna move out here.
Oh, this one. Oh, yeah, it's the after you do this one first because of the exponent.
Because it's an exponent.
Yes, okay,
If it's not an exponent in there, don't move it up.
okay, there's no exponent, don't move it out. Just move-
And there's a ton of worksheets online, conferences. If you're interested in doing this,
This method,
This is what we're missing.
the only thing I have is like, if. Using the graphical one, the graphic approach, it's a little hard because you don't know if that final mass. Is easy to solve, correct? If it's not in the same increments of
But it-
time? Or is it,
yeah, but I'm not gonna give you.
Oh, okay. they're
Practice,
not,
practice.
okay,
It's always gonna be.
the same
by two.
increments, oh, okay, okay.
And if you look at the formula for this, they don't have 0.5, they have 1/2.
Oh, it's 1/2, okay, oh, so it's same,
It's the same, but it's. It isn't, it isn't. The 0.5 is real easy, it's just a number, where 1/2 is a number also, speaking of 0.5. Because the exponent is in a fraction, it works to. That's why I didn't make it a fraction, I just put 0.5.
oh, okay.
So if you look that up online, this number will be.
Okay.
What's that 34? What's that 34? 34.
All right. There it is, well, this,
Okay, okay.
so this seems a little, awful.
See,
I wanted to make sure everyone saw the heads and the further time. And I'm. You understand the concept of that life. So using the graphical design of things. You see how it's going down by half. When you go through the half life in time. Always is by half. Okay, I'm gonna cover. I'm gonna cover one more thing, and that's equilibrium. Now, chemical equilibrium is fundamental. You take, I forgot, this code is 400 or 401. They do that for 2.5 weeks, equilibrium. And all the fancy formulas and whatever. We're not gonna spend 2.5 weeks on equilibrium. We're gonna spend a lecture on it. All right. Okay, so to understand equilibrium, we have to go back to our, I showed you this, this will be the third time on that graph. Uh, I think I'm gonna cover this tomorrow. We're gonna end this lecture. This is crazy.
See,